a basis. Let me start with two-dimensional space. Suppose the space, say, example. The space is, let's make it R3. Real three-dimensional space. Give me one basis. One basis is, so I want some vectors. Because if I ask you for a basis, I'm asking you for vectors, a little list of vectors. And it should be just right. So what would be a basis for three-dimensional space? Well, the first basis that comes to mind, why don't we write that down? The first basis that comes to mind is this vector, and this vector. Okay. That's one basis. Not the only basis. That's going to be my point. But let's just see, yes, that's a basis. Are those vectors independent? So that's like the x, y, and z axes. So if those are not independent, we're in trouble. Certainly, they are. Take a combination, C1 of this vector plus C2 of this vector plus C3 of that vector, and try to make it give the zero vector. What are the C's? If C1 of that plus C2 of that plus C3 of that gives me 0, 0, 0, then the C's are all 0. Right. So that's the test for independence. In the language of matrices, which was under that board, I could make those the columns of a matrix. Well, it would be the identity matrix. Then I would ask, what's the null space of the identity matrix? And you would say, it's only the zero vector. And I would say, fine, then the columns are independent. The only thing, the identity times a vector giving 0, the only vector that does that is 0. Okay. Now, that's not the only basis, far from it. Tell me another basis, a second basis, another basis. So, give me, well, I'll just start it out. 1, 1, 2. 2, 2, 5. Suppose I stop there. Has that little bunch of vectors got the properties that I'm asking for in a basis for R3? We're looking for a basis for R3. Are they independent, those two column vectors? Yes. Do they span R3? No. Our feeling is no. Our feeling is no. Our feeling is that there's some vectors in R3 that are not combinations of those. Okay. So suppose I add in I need another vector then, because these two don't span the space. Okay, now it would be foolish for me to put in 3, 3, 7, right, as the third vector. That would be a goof, because if I put in 3, 3, 7, those vectors would be dependent, right? If I put in 3, 3, 7, it would be the sum of those two. It would lie in the same plane as those. It wouldn't be independent. My attempt to create a basis would be dead. But if I so what vector can I take? I can take any vector that's not in that plane. Let me try. I hope that 3, 3, 8 would do it. At least it's not the sum of those two vectors. But I believe that's a basis. And what's the test then for that to be a basis? Because I just picked those numbers, and if I had picked 5, 7, minus 14, how would we know? Do we have a basis or don't we? You would put them in the columns of a matrix, and you would do elimination, row reduction, and you would see, do you get any free variables? Or are all the columns pivot columns? Well, now actually we have a square. The matrix would be 3 by 3. So what's the test on the matrix then? The matrix, so in this case, when my space is R3 and I have 3 vectors, my matrix is square. And what am I asking about that matrix in order for those columns to be a basis? So in this for Rn, if I have n vectors give a basis, if the n by n matrix with those columns is what? What's the requirement on that matrix? Invertible. Right. Right. The matrix should be invertible. For a square matrix, that's the perfect answer, is invertible. So that's when the space is the whole space Rn.